Our third dynamic programming example is another one of the classical examples for dynamic programming, and that is the knapsack problem. Now, the knapsack problem is one that you might have heard of in the first time you've heard of it as something that is an NP-complete problem. And most people, when you think NP-complete, you think something that takes exponential time. And yet dynamic programming, it feels like this is just polynomial time. We usually just have a couple of loops or something like that. Why would knapsack be NP-complete and us be able to have a polynomial time solution for it? And the reason is the way that you define the input is the size of the input. And you can think of that as sort of the number of bits that you need to represent a number and not the value of the number itself. So if you have something that increases in size, in other words, if you need another bit to describe the input, that's going to double the amount of time that this approach that I'm about to describe would take. And so sort of every bit that you increase the input, that's going to increase one of these values. It's going to basically be doubling it. And so that's where you get that kind of the way people think of NP-complete problems is they have this exponential growth, and you're doubling every time you just add one onto the number of bits that you need. But normally you don't think of knapsack in terms of number of bits. You think of it in terms of the value that it has, in terms of the size of the knapsack. And when you think of it in those terms, yes, it is going to be polynomial time, as we'll see here. So first of all, let's define the problem very clearly. So the knapsack, you assume that you have some knapsack of size X, and you can think of this as if you're, Indiana Jones and you have a sack and it can hold a certain amount of weight. So X is the amount of weight that your sack can hold, and you go into a treasure room and there's all this treasure in there. And basically you have a set of items, and we'll call those items 1 to n. And each one of them is going to have a value of the value of the item X, and it is going to have a particular weight. And so this is going to be the value of item X. And I shouldn't have maybe used X. Let's use I here. So V of I and W of I. So it's going to be the value of item I and the weight of item I. So what we want to determine is how much value can we carry out in our knapsack of size X, given this set of items from 1 to n that have various values and weights. So we will set this up as a dynamic programming problem. And if you haven't seen the earlier dynamic programming examples, particularly the one involving coin change, I would encourage you to look at that first, because I go through a little bit about how I'm going to define all of these terms. But basically, we're going to have a 2-parameter problem again. And we will have A and B. And I will define this to be the maximum value possible for a knapsack of size A, and where items 1 through B are available. And unlike the coin change problem, we notice we have a maximum instead of a minimum here, although that's not on its own all that different. Each item can only be used once, and we're not just counting how many items we have. Each one has a particular value associated with it. Okay, so now we define our recursion. First of all, we can think of some of our base cases. So if we have dp of 0 or B, in other words, if we have a knapsack of size 0, then obviously the value that you can get out of it is 0. And along with that, if you have a knapsack of any size, but you have no items available, you can't get any value out of that. And if you want to think of it, there's different ways you can do this in terms of your coding, but at least conceptually, if you ever have something where you have some sort of negative value. So if you have a negative size knapsack for any number of items, we want to set that equal to minus infinity because this is something that we don't want to allow happen. We can't ever have a negative value knapsack. So these are kind of our base cases. And now we want to define our general recursive case. So dp of AB. And we basically have two options. If we're faced with a set of B items and a knapsack of size A, and we want to write this as something with a smaller, remember that we want each parameter to go down, well, we can basically either choose to take item B or not. Those are our choices. Either B is going in the knapsack or B is not going in the knapsack. So what we're going to have is the maximum of two different cases. So the first one is if I go ahead and I take item B. So if I take item B, then I'm left with a new problem at the end of this. And that means that my knapsack originally had A in it, and now it's going to have weight of B that's used up. And so I'm left with something that's of size A minus the weight of B. That's how much room is left in my knapsack. And obviously, I've now used item B, so only the smaller items are available to me. But out of this, I got the value of item B. So whatever item B's value was, now I've gotten to enjoy that. So this is the first case. This is where I actually take item B. The other case is where I don't take item B. I just say, nope, I'm not going to take it. Not worth the weight that it has. And so I still have just as much room in the knapsack as before, but now I'm considering just fewer items. And that's the only thing that I need in the dynamic program itself. Now, I will say that in this type of problem, if you want to then reconstruct the answer, and I'll try to illustrate this at the end, you often want to annotate with which of the two choices you wanted. So let's just call this choice 1, which is you take that item, and choice 2 is you don't take the item. So those are the two choices that I have there. And if every time that I make a choice, once I figure out which one is the maximum, I probably want to record and say, is it choice 1 or choice 2, so that I know anytime that I had choice 1 on something, that's when I took the item. And if it was choice 2, I didn't. Okay, well, I'll illustrate an example of what this would look like in the end, but I'm not going to go through all of the detail in it. I assume you can do that by now, but I will illustrate it so that you can verify what this table looks like yourself. And I will highlight maybe 3 of the cells or so and see what they look like. So let's assume that we have a knapsack of size 6, and we have a set of items. And for each one of them, each one has a value V, and it has a weight W. And let's say, just to make life easy on ourselves, although they do not have to generally be like this. Let's say that they have weights 1, 2, 3, 4, and 5, and they have values of something like 2, 5, 6, 10, and 12. Okay, and this was number 1, 2, 3, 4, and 5. So those are my 5 items of weights 1, 2, 3, 4, and 5. Now, I'll mention they don't have to be in sorted order. You could have done this in an arbitrary order, as long as it's consistent. And the weights don't have to they don't have to be increasing. Anyway, you've got that set. So we would have a table here then that we will set up. Okay, and go 0, 1, 2, 3, 4, 5, 6. So this is going to be A, and I'll just note that this is different from the way I drew the table last time. And this part up here will be B. Okay, and I will have, I guess I'll go ahead and start it labeled at 0, 1, 2, 3, 4, and 5. Okay, since there's 5 items. Now, our base cases, just like we had before, all of these are going to be zeros. In other words, if there's no items or if there's no weight in the knapsack, all of those are 0. Okay, the thing that we are going to be looking for is going to be dp of 6. Knapsack size is 6, and there are 5 items. So we're going to be looking for dp of 6, 5, and that is this cell down here at the very bottom. So I'm just going to skip ahead. I'm going to show you some of the values that get filled in. I will point out that notice in our recursion all the way up here that every time we do the recursion, we're looking at b less than 1. So that means that we probably want to figure out, if we're on one column, we want to have figured out the previous column first. So that means that it would make sense to kind of work column by column from left to right and then from top to bottom as we go, and fill in our table that way. That way we're always guaranteed that we saw the column that we need beforehand. So I'll go ahead and fill in some of these values just so you can see what they are. And some of this will be obvious. Obviously, if we have item 1 that had weight 1, as soon as we have a knapsack that can hold 1, we're going to include it. So all of those are going to be the value 2. Once we get up here to something of size 2, well, if it can hold 1, we'll take the item of weight 2. Here we take the item of weight 5. So let's illustrate one example here and check this one out. So I'm going to look at this cell right here and determine what it should be. So notice that our check over here is we are wanting to find dp of 3, 2. Okay, and so that's going to be the maximum of 2 possibilities. So the first possibility is going to be dp of 3 minus, and the weight of item 2, well, the weight of item 2 is 2. So they'll take 2 and b minus 1. That's this up here. So first of all, it was 3 minus 2, and then 1. And then plus the value of that, which the value of item number 2 is 5. Okay. And this, if we look at it, this is equivalent to dp of 1, 1 plus 5. And if you look at dp of 1, 1, that is this value right back there, which is 2. So this is 2 plus 5. Which comes out to be 7. Okay, so that's our first option. So choice number 1 is 7. If we had choice number 2, this would be dp of 3, 1. And so we can look at dp of 3, 1. That would be that one right there, and that's just a value of 2. And so clearly we want the value of 7. So our answer here is going to be 7. And we made choice 1. So we'd probably want to annotate this with some sort of like little 1 or something like that, just so that we knew that it was choice 1. And you can store that in a separate table. You can store which choice was made. Okay, so if I were to go on and sort of keep filling all of these things out, we would get values like that here. The next row, again, I will just jump forward and show you some of the values along the way. Okay, I'll do 2 more examples. I'll do this one and the final one. So there's this example right here. So let's just walk through the steps in that so you can see them. In this case, we're wanting to compute dp of 5 and 4. And that's going to be equal to the maximum of 2 things. So the first one is going to be dp of 5 minus the value of 4, which would be 5 minus 4, or 1 and 3. plus the value of item 4, which is 10, and so this then becomes dp of 1, 3. Notice that we are looking at all the way back here to 1, 3 in this case. So that's going to be 2. So this is going to be 2 plus 10, which is 12. The other option is dp of 5, 3. That's this option over here, which is 11. So the maximum of those two is 12. And that again was a choice of type 1. Okay, so we were looking at this one all the way up here and saying that plus 10 is 12, or we were looking at this one, which would be, what if we did not take the item of weight 4? We just took the remaining items, and the best we could do that way is 11. Well, again, if we keep going on and filling things in, we will end up with lots of different values. And let's look at our final one for when we compute the final dynamic programming example. So this will be dp of 6, 5. And that's going to be the maximum between dp of, again, since item 5 happens to have weight 5 in this case, it will be 1, 4 plus whatever its value is, which is going to be 12. And that dp 1, 4, that is this element up here. So this is going to be 2 plus 12, which is 14. And the other option is we do dp of 6, 4. And that is this element right here, which is 15. And so in this case, the maximum is 15. And that's going to be the most that we can get out of our entire knapsack. And notice that this time it was a choice of type 2. In other words, we were better off not taking the item of weight 5, even though it had a nice value of 12. Instead, we don't take that, and we just use items 1 through 4 to fill our knapsack of size 6. And each of those we could look. It turns out that we do take, I believe, items 4 and 2 to get our 15 is where that one came from. Okay, so that's an illustration of another problem, the knapsack problem. Again, just like we had before, the key to all of this is trying to figure out what should my parameters be, how can I actually define my dynamic programming function, what does it mean, and then coming up with your base cases and your recursive case for every subsequent dynamic programming result. And then once you have that, it's just a matter of basically filling in the table, and each part of that is a very simple calculation.